Hey guys, example 3 here, and this time we're going to find the Maclaurin series expansion for f of x equals cosine x. But we're not going to do what we did in example 2 and reinvent the wheel. Instead, we're going to cheat, and this is how. Remember, we labored so hard in example 2 to show that the Maclaurin series for sine is what's written right here. And we remember from our very first lessons in calculus that sine's derivative is cosine. That is, cosine is the derivative of sine. So why don't we just do this, which is take sine and take its derivative. Because if we do that, first let me make some space here. Just slide this a little to the right so I can write a ddx in front of it. Remember, ddx means take the derivative of whatever is written after it, right? So ddx of sine is cosine. But that's the same thing as ddx of this infinite sum here, right? And so then, again, once I take derivative on the left side, I get the derivative of sine is cosine x, right? And then on the right side, I get that the derivative of this infinite sum is going to be the sum from n equals 0 to infinity, and then it's going to be negative 1 to the n. Think about why this does not change, even though I took a derivative. But it's negative 1 to the n, and then here I apply the power rule for taking derivatives. So I write this times 2n plus 1, right, times x to 1 less power than it had before because I just took a derivative, or I am taking derivatives, right? So x to the 2n power, and then the denominator I just keep as it was before, right? Just applied the power rule for derivatives. But in the denominator, I'm going to choose to rewrite 2n plus 1 factorial as 2n plus 1 times 2n factorial. Now, this here is exactly that, so I didn't do anything wrong, right? But look at this now. I could do this. Boom. Boom. And so then I see that the closed form for the Maclaurin series for cosine x is going to be the sum from n equals 0 to infinity of negative 1 to the n, and then it's x to the 2n power, and then it's going to be divided by 2n factorial, right? All this divided by 2n factorial. There we are. That's the Maclaurin series for cosine. Wasn't that nice and cheap and simple? It was. Now, I will clarify one point, which is why we keep the negative 1 to the n power the same and why we still go from n equals 0, why those things do not change. Remember, sine x, before we took the derivative, was like everything here in black, and yeah, on the left side, obviously, just sine x. But yeah, if we write sine x term by term, right, the Maclaurin series for sine x, it will look as follows. Sine x will equal, I start with n equals 0 and just interpret this sum here, right? Ignore that and that, basically. Yeah? Okay, so sine x is equal to, n equals 0 is going to give me x, right? And then I'll have minus x cubed when n equals 1, x cubed over 3 factorial, and then it's going to be plus x to the 5th over 5 factorial, and then minus x to the 7th over 7 factorial, and then plus dot, dot, dot. So if you had trouble seeing how taking the derivative of this works, then you can just take term by term derivative of these guys, derivatives of these guys, and then see that you'll get the same Maclaurin series that I claimed for cosine, which is what I just circled down here. Yeah? Okay, let's do it. So if I take the derivative, ddx of the left side here, same as taking the derivative of this infinite sum, right? And I'm going to take the derivative of the infinite sum on the right side term by term. So ddx, ddx of all of this. But what is that? First, sorry y'all, let me get rid of this. Some of you probably got what I'm about to point out and were long gone, which is okay. But yeah, this is for the students who might find this helpful. And so look here. Slide this up here. And now, obviously, as I said already, ddx of sine x is cos x. So I have cos x on the left side, but on the right side, what's the derivative of this? That's 1. And then minus, and then I'll have, by the power rule, 3 times x squared over 3 factorial. But the 3 here and the 3 factorial are going to cancel to a 2 factorial in the denominator. So I prefer to write that. So I just have minus x squared over 2 factorial. And then I'll have the next term plus x to the 4th. I'm just skipping details over 4 factorial. Like similar stuff to what happened here will happen once you apply the power rule, right? And then minus, and it's going to be x to the 6th over 6 factorial. So you see, first, if I let n equal 0 in this expression, what do I get? I get negative 1 to the 0, which is 1, and then I get x to the 2 times 0, so x to the 0, which is 1. So this whole thing is 1 when n equals 0. And then here I get 0 factorial, which is 1. So I do get that. And then I want this to be positive, just like how that was positive. That's the reason why I do not tamper with that. Yeah? All right, cool. The rest is, I think I've explained sufficiently. All right, cool. More examples to come. Keep watching. We're going all the way to example 7.